0, then the voltage that we would measure over this battery, which is VB minus VA, for which I will simply write down V of the battery, that voltage we call a curled E, which stands for EMF, which is electromotive force. I will show you that later. If I put a resistance R in here, which is not infinitely large, then the current will start to flow. But now, we should never forget that between the point A and B, invisible to the human eye, there is always an internal resistance, which I call little r of I. And so if a current starts to flow, it goes not only through capital R, but it also goes through this little r. And so according to Ohm's law, the EMF is now I times the external resistance plus the internal one. The voltage that you would measure between point B and A is now going to change. That voltage, according to Ohm's law, is IR, and so it's also the EMF minus I times R of I. And you see it's a little lower than the EMF. And the reason is this internal resistance here. If I shorted out this battery, stupid thing to do, but if I make R equal 0, so I take the battery and I just short it out, then the maximum current that I can draw then, so R is now 0, so you can see that the maximum I that you can get is E divided by R of I, and V of B, the voltage that you would measure now between point B and A, goes to 0. It doesn't mean that there is no current running, but it means that between these points, your potential difference goes down to 0. Shorting out a battery, of course, is not a very smart thing to do. You can put batteries in series and thereby getting a higher potential difference. If this is the negative side and this is the positive, I have an independent one, negative, positive, and an independent one, negative, positive, each one with an EMF E, then I can connect the positive side of one with the negative side of the other, just a conducting wire, and the positive side of this with the negative side of the other, and now the potential difference between these 2 points is now 3E. Open circuit, if I don't draw any current. If I draw a current, then of course I have to deal again with the internal resistance. I'm going to build with you a copper zinc battery of the kind that we just discussed. You see it here. Here's the copper sulfate solution, which H2SO4. And here are my plates. This is my zinc plate, and this is my copper plate. And you are going to see the voltage displayed, I think over there, that is correct. There is no potential difference now, because they're not in place yet. And so here comes my zinc, and here comes my copper. And they go into the solution, and you see about 1 volt. In general, these potential differences are of that order of 1 volt, 0.95. So now what I will do, I'm going to create a double one. So I have 2 independent batteries. I have here one whereby I have copper and zinc, and I have another one whereby I have copper and zinc, and I'm going to connect this one, and you will see now that the EMF will double. If we're ready for that, this is my second one, is going to be completely independent. So here comes the other two plates. Make sure that I have the copper and the zinc not confused. There we go. And now you should see twice the potential, and you do see that. It's open circuit, there is no current running. Well, there is a minute little small current running through the voltmeter that you see, but that's so small that that can always be ignored. And you see you get double the EMF. Now what I will do, so I have now about 2 volts between these two plates, 2 batteries in series. I now have a little light bulb here, and I'm going to turn on the light bulb. And now what you will see is that the voltage that you measure right here, that's all you can do. You can only measure the voltage at the plates of the battery. That now this voltage will drop because of the internal resistance of the battery. In addition, you will see some light, but that's really not my objective. For those of you who are sitting close, you can see this light bulb is going to be lit. So I do this now. I can see the light bulb, a little bit of light, and notice that the voltage goes down. And so this value that you measure now, V of B, is now lower than the 1.9 volts because of this term. You lose inside the battery through the internal resistance. You lose their potential difference. All right? So let's take this out because this produces a lot of smelly fumes. Okay. That's fine. If a charge moves from point A to point B, and here the potential is VA, and here the potential is VB, and a charge dq moves, and let's suppose for simplicity that VB minus VA, yeah, let's make VA larger than VB. That's just a little easier to think in those terms. It's not necessary, of course. So let's make VA larger than VB. So the electric field is from A to B. And I move charge from A to B, then the electric field is doing work. And the work that the electric field is doing, dW, is the charge times the potential difference, which is VA minus VB. This work can be positive if the charge is positive, can be negative if the charge is negative, because we have assumed that this is positive in this case. I can now do something that you shouldn't tell your math teachers, but physicists do it all the time.